So reaction mechanism 14 involves combining some chemistries that we've already seen. So we're going to talk about the fact that the alpha carbon is acidic, and we learned about that in reaction mechanisms 8 and 9. And again, in 8 and 9, what we did is we deprotonated the alpha carbon's hydrogen, but because there was an alpha hydroxy group, that allowed us to sort of interconvert the alpha hydroxy aldehydes and alpha hydroxy ketones. But in this situation, what we're going to see is not kind of doing this sort of proton shuffling around to move where a carbonyl group is. We're actually going to use the enolate that we generate, that negatively charged intermediate, which again is going to allow that to be nucleophilic, to react with another molecule that we know to be electrophilic. So again, another carbonyl containing molecule. So again, the easiest way to know the chemistry that happens here, that is who is a nucleophile and who is an electrophile, is to look at the product. That is, we have a beta hydroxy ketone. So the ketone must have served as our electrophile in this case, and the aldehyde must have served as our nucleophile. So hopefully this is going to make sense as we walk through this mechanism. I'm going to kind of highlight some things within the mechanism here, and then we'll have a good bit of discussion here on some commentary and connection. So if we take and we have a generic aldehyde here, and I'm going to expand this from what we normally might write with an aldehyde, and that I want to show the alpha carbon's hydrogen because we need to be able to deprotonate this. So again, deprotonation of this alpha carbon. That's acidic again because if I initially show putting those electrons on this carbon, we're going to generate this carbanion intermediate. That is going to be resonance stabilized by moving these electrons through to the oxygen atom. Whoops, wrong arrows. We have to make sure we draw our resonance arrows here. So this is resonance stabilized as this enolate intermediate. And we've talked about with this resonance stabilized intermediate, so this resonance stabilized enolate intermediate, it has the potential to be a nucleophile. So what we're going to see here is now we're going to have a ketone, an aldehyde here that's going to be acting as our electrophile. So to highlight here, we've got our ketone as our nucleophile, which that's the one that we're going to be deprotonating the alpha carbon from to generate our nucleophilic intermediate. And so our aldehyde is going to be our electrophile, specifically this carbon here. Now again, the only way that we know that is the fact that we maintain this ketone functional group. This isn't a beta hydroxy aldehyde, it's a beta hydroxy ketone. That must mean that we generate our nucleophile from that ketone because we are going to be maintaining the carbonyl on the ketone. Okay, so coming back to our mechanism here, what we're going to see is now we're going to have this resonance stabilized intermediate act as a nucleophile. And what's going to be interesting, and I'm just going to highlight this here, even though the negative charge right now resides in this oxygen because it is the more electrophilic, electronegative atom, sorry about that. It is the more electronegative atom, so we're better putting the negative charge on that atom for our resonance structure. What we tend to see is we tend to reform this carbonyl and then have chemistry as though this carbon was the nucleophile. And that's because putting those electrons back in our double bond here between a carbon and oxygen is going to be more stable than keeping the double bond here between our two carbon atoms. So now drawing this out mechanistically, we're going to reform our carbonyl. These electrons here are going to now go and act to nucleophilically attack our electrophilic aldehyde here. So the net product that we get, and I'm going to highlight this on the next slide, but early on here, let's make sure that we sort of keep things in the same relative orientation, because one of the things that can become difficult here, particularly if you start doing reaction mechanisms with skeletal structures, is it's very easy to lose carbon atoms. So for right now, I'm just kind of keeping This guy that was the nucleophile in the same relative position, the guy that was the electrophile in the same relative position. And when we have nucleophilic attack on a carbonyl containing carbon, we generate a tetrahedral intermediate. And when that carbonyl containing compound was an aldehyde or a ketone, like we've seen with previous mechanisms, there's no good leaving group here, so we're not going to decompose that tetrahedral intermediate because there's really not a good leaving group unless we consider this guy coming off as a leaving group, but then we're moving backwards here, and that's not what this mechanism is about. So again, the only option that we have here is to protonate this alkoxy intermediate. And so we're going to have what we'd refer to as a general base here, or I'm sorry, general acid, being able to protonate and then generate our final product. And I'm going to sort of rearrange things and kind of make them look a little prettier here. I'll go draw it slowly so we can kind of see where pieces come from. So here's our R double prime. We're going to have this carbon, which is attached to a hydrogen, and now that OH group. Okay, so I've got this piece now right here, and now I'm going to take this guy and I'm going to kind of move them up so they're all sort of in our main carbon chain is in the same line here. So now we've got a carbon attached to a hydrogen that's attached to an R group, and then there's our existing ketone, which we never really did any chemistry with. So let me kind of go through here and highlight where our parts are. So these atoms are these guys, and then these guys are now here. So again, very easy to sort of lose carbon atoms, especially like I said, if you're doing some skeletal structures. So I encourage you, especially early on, draw out all your atoms here. Keep things when you first do chemistry in sort of the relative positions that we see here. So lots of comments. I have a couple pages of comments here that I want to comment on this because this is sort of a new mechanism. This is the first time that we've done something kind of important here, which is to show the formation of a new carbon-carbon bond. And so this is important because carbon-carbon bond forming chemistry is going to be an important part of anabolic metabolism. So carbon-carbon bond forming is going to be really important for anabolic processes. And so likewise, we're going to actually see that breaking this bond is going to be important. And so kind of learning to recognize that this kind of a bond represents a latent bond. So let me highlight in our second structure here. It's this bond. And so this bond is an alpha beta bond. Okay, so again, this is the alpha carbon here, this is the beta carbon here. So that bond between the alpha and the beta carbons is what we call labile. It means it's easily broken. And so one of the things that's going to be important for us to think about is as we look at these molecules is recognizing that that's kind of a hidden break point if we need to be doing catabolic processes and sort of breaking things apart. Again, anabolic is a little bit easier to see as we're going to be kind of putting these things together. So a few comments here, and I'm going to kind of highlight and reflect back to a couple of other mechanisms. Again, this is sort of a new step mechanistically compared to some things we've seen before. And again, this kind of combining chemistry, as I highlight here, is often the most difficult to see and keep track of atoms. So as we did in the mechanism here, consider keeping atoms in your molecule in the same orientation. Maybe rearrange them only in your final product to kind of have all of your carbons sort of in a main chain. And probably a term that you remember from organic chemistry is this is called aldol addition. So again, people mistakenly think that aldol chemistry must involve reaction between two aldehydes, one being deprotonated at the alpha carbon serving as the nucleophile, the other serving as the electrophile. And again, this is the truest form of aldol addition and why it was given its name, but the chemistry can actually have happen in 3 other flavors. Again, we could have each functional group serving as either an aldehyde, the nucleophile or the electrophile, and so we sort of have the ability here to have 4 possible combinations. We have an aldehyde as the nucleophile, an aldehyde as the electrophile, which is the truest form of aldol addition, or again, you can have The aldehyde is a nucleophile, and the ketone is the electrophile that's going to generate a beta-hydroxyaldehyde. Remember, whoever is your enolate, we're going to retain that as the carbonyl-containing functional group. Ketones as the enolate reacting with aldehydes will give us beta-hydroxyaldehydes, and we're also going to get beta-hydroxyketones if we have two ketones reacting. Again, I didn't give you all of these permutations as mechanisms to kind of think about. Make sure you could do them. Again, that's sort of fair game for something that I could give you is one of these mechanisms for one you haven't seen, but it's essentially doing this aldol chemistry. Last thing to kind of comment, the only way that you sort of know that this is the chemistry that's going to happen is you see what the product is. One other thing to sort of highlight, and let me kind of flip here to reaction mechanisms 8 and 9, just as comparison here. When we look at reaction mechanism 8, we were still deprotonating the alpha carbon of a carbonyl containing compound, but what made this unique is we had this hydroxyl group on the alpha carbon as well, and that allowed us to generate this enediol intermediate, and then from there sort of do a rearrangement to put the carbonyl on an adjacent carbon. And so what makes this mechanism different is the ability to kind of have this hydroxyl group participate in chemistry, but at the start they both start out the same by having this hydrogen atom on the alpha carbon being acidic. All right, so coming back here to sort of finish out the notes on this mechanism. Again, biochemically, what's the application that we have here? There's lots of carbon-carbon bond forming chemistries. This is kind of an important one that we're going to see. Again, we're going to spend a lot of time discussing fuel metabolism as either catabolic processes, meaning we're breaking things down, making smaller molecules, or anabolic. We're going to be doing some bond making. So this type of a carbon-carbon bond forming chemistry is going to be really important. We didn't talk about this too much in class, but this kind of chemistry, this sort of Aldol addition, is how collagen fibers can be cross-linked. Again, context for this, which we didn't have time to talk about in class, but collagen fibers can be cross-linked to one another, much like we talked about keratin fibers being disulfide linked, and that kind of imparts curliness or straightness to hair. Collagen fibers can also be cross-linked, and that actually contributes to the sort of toughness or not so much toughness in meat tissue. And again, this chemistry that happens with collagen cross-linking has to do with what we call the epsilon amino group. So it's that amino group on the fifth carbon out, alpha, beta, gamma, delta, epsilon. So the fifth carbon atom out on the amino acid side chain is going to have an amino group with lysine, and we're going to use that that essentially to do an aldol-like condensation with an aldehyde. This lysine is actually converted into an aldehyde, and then we're going to condense two of them together to cross-link two collagen strands. So some interesting biochemistry that we didn't necessarily talk about, but again, we can have some functional group conversion by converting that lysine's amino group into an aldehyde, and then we can have an aldol condensation to cross-link collagen fibers.